Okay, so we finally got to the point where we can talk about the electronic structure of transition metal complexes. And so this is important because this dictates what color they are. So we said that they're very strongly colored, dictates their redox behavior, dictates their reactivity, dictates their structure. So I mentioned before that the geometry of what the complexes are is determined by the d count. And that's determined by how the electrons are filling into the d orbitals. And that governs the final stability of your structure. So to address the question of bonding in transition metal complexes, there are kind of two major approaches, and they're both really similar to each other. So in this class, we'll use them kind of interchangeably. So it's crystal field theory and then so this approach treats all your ligands and your metal as point charges. So, oops, okay, excuse me. This is point charges. So you imagine that your ligand, which has, of course, delta minus, it's doing a dative bond to Lewis base, and that's coming in, and that's going to perturb the energies of your orbitals in your metal by which direction they approach from in the structure of your molecule. If we add a secondary component of like covalency and kind of like molecular orbital aspect to it, then we get what's called ligand field theory. Ligand field theory. So I'll start off with kind of the general idea of crystal field theory, and then we'll move to ligand field theory and have kind of a general approach to both. So it'll be kind of hybrid. I'll use these terms interchangeably, but the overall final results of what we expect to see is still pretty much the same. So the takeaway will be the final pictures of the orbital diagrams that we draw. Okay, so let's start with crystal field theory. So the idea is like if you have point charges, so suppose you have an octahedral complex, so Ml6. Okay, so then my ligands are all coming down these positions. So I have my point charges all in these directions. So these are my supposedly negatively charged ligands. Okay, so they're coming down this way, and so they're approaching the metal. So again, here's where the orientation of your orbitals really matters. So I'm going to draw kind of my coordinate system here. So z, x, y. So what we know is that if we have these point charges here, and then we know our orbitals are going to end up looking like, so with this coordinate system, our orbitals are, oh, that's a bad marker. Okay, so this is dz squared. And then the same system, we have, let's say, dx squared minus y squared. We have dxy, which is where the x and y axes are in between the lobes. So dxy looks like this. So it's different than dx squared minus y squared. Oops, excuse me. Try to keep everything on the same level here. Minus y squared dxy, and then we have xz. Again, x and z axes are going kind of like in between and down the nodal planes. And then dyz going kind of into the board this way. Okay, so if we think about the ligands approaching these orbitals down these axes that I've drawn, what we see is that the 6 ligands are down each the z, x, and y axes. So if we think about what the ligands can interact with, ligands over here can interact very well with the lobes of this guy, and these ligands over here can also interact as well with the donut. Okay. So this is kind of the point charge aspect of it. If we were to do kind of like the more MO aspect of it, we could make bonding, anti-bonding orbital combinations. So I'll kind of draw like that as like a mini version down below. So here's my dz squared orbital. I could form a bonding combination. It's looking like here. And then these guys would be the same phase, so shaded in. So this would be a bonding combination of your ligands with the dz squared. So there's really good interaction here. For the dx squared minus y squared, we could do the same thing. So these equatorial ligands in the xy plane could interact very well because, again, these lobes are pointed just down the x and the y axes, so we could form a bonding combination this way, or put point charges. So I'll just draw that one. So here's kind of like the MO version. And then so we have really good bonding with these equatorial ligands. Unfortunately, well, not unfortunately, but these axial ligands are right down that nodal plane of the dx squared minus y squared, so the axial ligands do not interact. So I'll kind of put them as just like dots for now. They're not really interacting. But still, we have very strong interactions here. So because these lobes of the dx squared minus y squared are pointing directly at our ligands. So actually, overall, the interactions between these two are actually about the same, because here we have 4 very strong interactions. Here we have 2 very strong interactions with these lobes, but the donut's not really quite pointed at the equatorial plane as much. So overall, it averages to about the same. OK. So for the dxy, dxz, and dyz orbitals, all our ligands are actually pointed down the nodes of these orbitals. So there is no interaction for when you think about point charges, or if you think about kind of sigma bonding s orbitals here. So these guys, no interaction. OK, so as a result, what we end up having is that we have 2 d orbitals that can interact with these kind of sigma bonding ligands, and 3 that can't. And so what the empirical, or I guess what's ends up happening is that we end up with splitting of d orbital energies due to our ligand field. So in class on Monday, is it Monday? Yes, Monday, we'll practice kind of doing this picture again with other types of orbitals. And in the next video, we'll talk about what ends up happening with the splitting of our d orbital energies.